Okay, this is going to be the first lesson in Unit 7, which deals with stoichiometry. All right, so we need to put on our remembering caps, and this is going to be from a long time ago. This is back before spring break. Okay, so we have to go back to balancing chemical equations. So hopefully you guys remember that. It's been, what, about 3 weeks maybe? So, in looking at this, we have to look and determine, what did that balanced chemical equation really tell us? Well, first thing, it tells us that this is a reaction, that when we combine these reactants together, they turn into the products. And so that's kind of the first rule, okay, is the fact that we know that this reaction occurs. Two, it tells us what things are the initial ingredients, the raw materials, the reactants. We know what is produced, the products. Okay, and this is kind of the most important thing. This next thing, we didn't really mention this before because you guys didn't know what moles were, but those coefficients are actually written in the units of moles. Okay, and so it tells us how many moles of each reactant and how many moles of the product are produced. So that's the main thing we're going to do. Not only that, but it also identifies the number of atoms or molecules for each reactant and product. We can calculate the mass from this. And then, it's that whole thing with the law of conservation of matter. So we're not creating elements, we're not destroying elements, we're just rearranging them in a chemical reaction. But the main thing is these coefficients, these numbers in front, those things are moles. Okay, so we've been working with moles and now we know what we're going to do with them. And so stoichiometry, this is kind of a weird word. But basically, all it is cooking with chemistry. It's a recipe. All right, it's telling me how many of the reactants I put together and how many products get pooped out the other end. Okay, so it is a calculation of exact amount of substances used as reactants, and you're able to predict how many products are produced, and that's it. That's what stoichiometry is. And so, like, here's an example. All right, if I use 2 cups of flour, teaspoons, I guess, of baking powder, 2 tablespoons of sugar, 2 cups of milk, and 3 eggs, that makes 12 pancakes. Okay, I know how many ingredients I need to put in. I know what comes out the other side, right? And so it's just telling us relative numbers of each. If I want to make as many pancakes as I can and I have an unlimited amount of all the ingredients with the exception of eggs, which I only have a dozen eggs, how many pancakes could I make? This is essentially stoichiometry. Okay, so I have all the flour in the world, all the baking powder, all the sugar, all the milk, but I only have 12 eggs. Okay, well, what you guys realize, you're like, okay, if I asked you how many pancakes you would make, what you would do is you'd use your knowledge of dimensional analysis. You say, okay, I've got 12 eggs, and according to my recipe, I need 3 eggs for every 12 pancakes. Right? Isn't that how that works? That's their ratio, 3 eggs to 12 pancakes, and I know I have a dozen eggs. Eggs cancel. So I'm going to take 12 times 12. That's going to be 144. And then I'm going to divide that by 3, and that tells me I can make 48 pancakes. Okay, and that makes sense, because if you think about it, if it takes 3 to make 12, well, I've got 4 times that amount. Well, it's basically 4 times 12 is 48, so it makes logical sense. But that's all chemistry is. It's just basically unit conversions. But we're not using pancakes and eggs. We're using moles and grams and molecules and atoms and all that fun stuff. Okay. So, when you look at this, the interpretation of the chemical equation, really what we're interested in are these coefficients. It's telling me how many moles of nitrogen, how many moles of hydrogen, how many moles of ammonia. It is a mole ratio. All right. I want you guys to jot this thing down. Okay, the mole map. This thing is going to be super important. It's very similar to our conversion, moles, atoms, and molecules and mass. It's just 2 of these kind of butted up next to one another, and there's kind of this mirror in between. And this is the key. This is the mole ratio. Every stoichiometry problem we ever do will contain a mole ratio. You're going to convert from moles of the known to moles of the unknown. Every one of them. There's no Stoic problems that does not contain a mole ratio. If you're doing one without the mole ratio, you screwed up somewhere. Okay? And so looking at this, you see very similar things. Okay? If I'm going from grams to moles, well, use molar mass again, using the periodic table. Okay, this part's new, the mole to mole ratio, but that's not bad. If I'm going from moles to grams, I use molar mass. Likewise, if I'm doing particles, this would be like atoms, molecules, that sort of thing. If I go from particles to moles, I use Avogadro's number, 6.02 times 10 to the 23rd, atoms in a mole, or whatever. And vice versa. If I'm going from moles to particles, there are 6.02 times 10 to the 23rd molecules in 1 mole. So mole map, very useful, very similar to the one we did last unit. It's just 2 of them, and they're married together here. They've got a little place here where they butt up, and this is the mole ratio. And every one of them will have this little bridge that we can cross from the known to the unknown. Okay, the mole ratio. Probably the easiest way to do this is just to demonstrate it. Oh, and honestly, here, I can put these on here. You can read through it if you want. I'm not going to go through and tell you all this stuff. I'm just going to kind of show you how it works. So if you want to write this stuff down and look at it, you can read it. I'm not going to sit here and read this paragraph to you. Let me scroll down here a little bit. There, pause that and write it down if you feel it necessary, but I'm just going to show you how it works. Once again, I'm not even going to do this part. I'm just going to get in here and do it. Okay, let's say I want to calculate the number of moles of iron 3 oxide produced if I react 7.3 moles of iron with excess oxygen. Okay, well, I'm going to tell you guys, the first thing you always have to do, the most important step, you have to have a balanced formula equation. You need a recipe, all right? If you're making pancakes, you don't go into the kitchen and just start grabbing ingredients and slapping them together willy-nilly. It's not going to turn out real well, okay? There is a tried and true method that it works. A series of various amounts of different ingredients, and you combine them and they come out. If you follow the directions, it works. If it doesn't, it doesn't. Okay? So we need a recipe. Real quick to balance this thing. I'm going to leave iron alone because it's all by its lonesome. 3 oxygens and 2. Common factor is going to be 6. I flop a 3 here and a 2 here. I have 6 oxygens on both sides. Iron now has 4. Put a 4 here. We're balanced. So step 1 is done. Balance the formula equation. Now, you start out with what you know. Well, it says we have 7.3 moles of iron. Okay? Well, if I know moles of iron, the other thing where it says excess oxygen, that means you have all the oxygen in the world, all right? It's not going to be the limiting factor. It's just like in our recipe. We had all kinds of sugar and flour and stuff, but we had limited eggs. Okay, so this is the same thing. We've got all the oxygen in the world. We have a limited amount of iron. Okay, and so I want to go from moles of iron to moles of iron 3 oxide. That's what the problem is asking. We're going from moles of this to moles of this, right? And so we're going from here to here. Well, let's go back and look at our equation here real quick. So I'm starting with moles of known. I'm going to moles of unknown. I need a mole ratio. It is a one-step Stoic problem. So I'm going to go back over here. Okay. Well, according to my problem, for every 4, I get 2. That's it. That's your mole ratio. If I'm trying to get rid of moles of iron, the moles of iron need to go on the bottom. How many? According to the balanced formula, I have 4. And then I'm trying to convert that into moles of iron 3 oxide. According to my balanced formula, I have 2 moles of iron 3 oxide. Moles of iron cancel. Guess what, guys? I'm ready to solve because I am at moles of iron 3 oxide. And so what I do is just like before. I'm going to multiply the numerator and divide by the denominator. So I'm going to take 7.3 times 2 divided by 4. Lo and behold, you get 3.65 moles. Now we have to observe sig figs because that only had 2. These don't count because those are not measurements. That is a definition. All right, those are exact numbers in that balanced formula. So we have 2 sig figs, 3.7 moles, and you should label this iron 3 oxide because we have 3 different substances here. So you should be telling us 3.7 moles of what. Well, that's as easy as it gets. I mean, that's all there is to it. Let's do one more, another mole-to-mole one, and then I'm going to give you guys some practice ones and give you an opportunity to do a few of these. Okay? Not bad. Let's see here. It says we want to calculate the number of moles of oxygen required to react with exactly 4.3 moles of propane. There it gives you the formula. And here's the following equation. This equation is not balanced. Let's see. I have 3 carbons, so if I put a 3 here, that fixes that. Let's see. 8 hydrogen, put a 4 here. That's going to fix that guy. Oxygen, 3 times 2, there's 6, and 4 more is 10. Put a 5 here, and we should be good. If you guys aren't good at balancing, you don't remember, you can go through and do your atom inventory, but hopefully you did not lose that skill because we're going to use it every day. Okay, I think somebody told you that, and I think that guy likes wearing plaid button-down shirts. It was me. Okay, so anyway, step 1, you got to be able to balance a formula. Okay, next. It says 4.3 moles of propane, so we're going to start with what we know, 4.3 moles. Propane is C3H8, okay? And it's asking number of moles of oxygen, okay? So we're actually comparing these two. Believe it or not, guys, these are all interrelated. You don't have to compare a reactant and a product. You can do a reactant to another reactant. You can do a product to a product. You can do a product to a reactant. They're all interrelated. Okay, so let's see. We're converting 4.3 moles of propane to moles of oxygen. So if I want moles of propane to go away, notice I have 1 here. I'm going to put 1 mole of propane on the bottom. And then on top, 5 moles of oxygen. Moles cancel. I'm ready to solve. Okay, so I'm going to take 4.3 times 5. And notice I don't have to divide by 1. When I do that, my calculator spits out 21.5 moles of oxygen. Notice I only have 2 sig figs in my measurement in the problem, so therefore my answer has to be 22 moles of oxygen. And that's it. Pretty straightforward. I'll do one last one here with you. Here's ammonia. It says it's used in quantities of fertilizer. It's manufactured by combining nitrogen and hydrogen. So here's the equation. It's not balanced. So let's see. Nitrogen, let's ignore that for right now. It's actually not going to matter either way, because if you do hydrogen, the common factor is 6. You're going to put a 2 here and a 3 here. That's going to give you 6, and then the 2 nitrogen balance. So 1, 3, and 2 are the coefficients. Okay, so it says I have 1.30 moles of hydrogen, and I'm converting this into moles of ammonia. So I'm going from here to here, right? Well, I need to get rid of the hydrogen moles, so I need to put 3 on the bottom according to the balanced formula. For every 3 moles of H2, I get 2 moles of NH3. Moles cancel. We're ready to solve because that is moles. I'm going to do 1.3 times 2. I'm going to divide that by 3. And my calculator spits out this 0.866666 repeating, right? Okay. I have 3 sig figs here, so my answer with sig figs would be 0.867, and this is going to be moles of ammonia. Okay, I'm going to give you an opportunity to practice these. I'm going to link a worksheet with a few mole-to-mole Stoic conversions. Just do them, practice them, and I'll give you the answers later.